Chapter 5, Electrons and Atoms. We are now in Section 3, Electron Configuration. We have talked about Section 1, the light and energy in electrons. Section 2, we talked about the quantum theory of the atom. Now in Section 3, we're going to specifically talk about electron configurations and where they are when we use all these principles. So, objectives for Section 3. Apply the Pauli exclusion principle, the Aufbau principle, and the Hind rule to write electron configurations using orbital diagrams and electron configuration notation. Define valence electrons and and draw electron dot structures representing the atom's valence electrons. And we have, in the entire chapter, been talking about what an electron is. It is the negatively charged particle with an extremely small mass that is found in all forms of matter moving through empty space surrounding an atom's nucleus. Okay, new vocab: electron configuration, Aufbau principle, Pauli exclusion principle, the Hind's rule, valence electrons, and the electron dot structure. Main idea: there are a set of 3 rules to determine the arrangement of electrons in an atom. Okay, remember we had talked about the ground state with the principal quantum numbers. The lowest energy level, or closest to the nucleus, is called the ground state. Okay, so we are going to use that to help figure out this electron configuration. Okay, the arrangement of electrons in an atom is called the electron configuration. The Aufbau principle states that each electron occupies the lowest energy orbital available. So if we have 4 principal quantum numbers, we need to make sure that the electrons are fill the lowest ones first. So we're going to fill N1 first, and then we're going to fill N2 first. They fill the lowest energy level available first. Okay, these are all of our energy levels here. We start with energy level 1, and remember these sub-levels within each level. So N equals 1 has 1 sub-level, N equals 2 has 2 sub-levels, N equals 3 has 3 sub-levels, N equals 4 has 4 sub-levels, and so on. So remember, it was S, P, D, and F for the sub-levels. So energy level 1 has 1 sub-level, so 1s. Energy level 2 has 2 sub-levels, 2s and 2p. Energy level 3 has 3 sub-levels, 3s, 3p, my mouse would stay here, 3p, and 3d. Okay. Energy level 4 has 4 sub-levels, S4, SP, 4s, 4p, 4d, and 4f. Now we get into the transition elements, and these have all new rules to themselves. Okay, so just realize that once we go into the 5th energy level, we have some different things going on. Okay? Okay, rules for the Aufbau diagram. Okay, all orbitals relate to an energy sublevel are of equal energy. Okay, so any of the electrons in one orbital have the same energy. So if they're all in the 2p, they all have the same amount of energy. In a multi-electron atom, the energy sublevels within the principal energy level have different energies. So if 3 2p orbitals are higher energy than the S2 orbital. So I'm going to go back here and we're going to look at that one. Okay, so you can see as this goes up the ladder, S1 is the lowest energy level, S2 has the next most energy, if you would like to say it that way, and then the 2p is just one rung on the ladder above that, so 2p has a little bit higher energy than 2s. Okay, so then we have the, so we have 1s, 2s, 2p, 3s, 3p, 4s, then we have the 3d, and then the 4p. Okay, so that's the way their energy levels go. Okay, in order of increasing energy, the sequence of energy sublevels within the principal energy level is, and you learned this last section, S, P, D, and F. So if n equals 4, then we have 4 sublevels, 4s, 4p, 4d, 4f. Orbitals relate to energy sublevels within one principal energy level, can overlap orbitals relating to energy sublevels within another principal level. So here's the example. The orbital related to the atom's 4s sublevel has a lower energy than the 5 orbitals relating to the 3d. So let's go back to our diagram and look again. Okay, so you can see that 4s, 3d has more energy than 4s. Okay, they can overlap like that. And when we look at our periodic table, we'll look at how that occurs. Next, we look at the Pauli exclusion principle. This states that the maximum of only 2 electrons can occupy a single orbital, but only if the electrons have opposite spin. So if you look down here, they have to have opposite spins. See how you have one arrow going up and one arrow going down? They must have opposite spins. Okay? The Hund's rule states that single electrons with the same spin must occupy each equal energy orbital before additional electrons with opposite spins can occur. Okay, so you're going to fill your 1s, you're going to fill your 2s. Now your 2p, so you have your 1s, your 2s, and now we're at 2p. So you must fill all of your up arrows first, and then your down arrows, you'll go back and refill those. So put your up arrows in first, and then go back and fill your down arrows. Okay, this is a really good diagram, and I really want you to go to glencoe.com and play with this and get this straight in your mind so you can see exactly how these diagrams relate together. So if you have, hydrogen has 1 electron, so it fills the 1s, so it has 1 up arrow. Helium has 2 electrons, so it fills up and down. Lithium has 3, so it fills up, down, and back up. Okay? Okay, noble gas notation uses noble gas symbols in brackets to shorten inner electron configurations from other elements. So remember, we're scientists and we're lazy and we're going to use shortcuts. So when we get down to sodium, we are going to use neon, which is the noble gas configuration, and we're going to put that in brackets, and then we're going to add the configuration to that. So sodium is 1 electron past neon, so we are going to have neon in brackets and then 3s1. Oops. Okay, the electron configuration for chromium, copper, and several other elements reflect an increased stability of half-filled and filled sets of s and d orbitals. Okay, once we get down here, we get into the transition elements, and they all act a little differently. Okay, valence electrons are defined as electrons in the outermost orbitals. These are the ones that are associated with atom's highest principal energy level. These are the ones that are related to the chemical reactions. With these valence electrons, we are going to do electron dot structures. These consist of the element's symbol, represented as the nucleus, and then dots surrounding it with the amount of valence electrons that we have. And you can see examples of this in this diagram as well. Please go to glencoe.com and play with this animation to get used to the information. Oop, gave you the answer. In the ground state, which orbital does an atom's electron occupy? The lowest available. The outermost electron of atoms are called. Answer is valence electron.